All right, this is a question from Module 6. We want to know the pH of a solution that is 0.49 molarity in sodium borate and 0.55 molarity in boric acid. If you're looking at this question on the quiz for you, it may be a different number. It may not be question 1, and you may have different molarities, but you will have sodium borate and boric acid. And that's the clue, that's the key when the question is, what is the pH of? I have two things in my beaker. They are sodium borate and boric acid. So the next thing I do is I identify what are these two. Boric acid is obviously an acid. Let's do the easy one first. It is not one of the strong ones I have memorized, so it must be weak, and I can further confirm that by looking at the Ka table. This is our table of ionization constants for weak acids. And I scroll down and I do indeed find boric acid, a Ka value. I've even got the formula there if I want to use it. And we'll talk about that in just a minute. But there is the Ka, 5.4 times 10 to the minus 10. So let's bring that file back and write that down. And I've already forgotten it. Let me double check that. 5.4 times 10 to the minus 10. Yeah, got it. We might need that in a minute. I'm writing it so that I don't have to go back. I could go back and get the formula for it, but with all of these weak acid and weak base problems, unless the problem specifically wants something about the formula, I can say that's a weak acid. I'm going to use the formula HA. There we go. All right, so that's one of the things in the beaker. The other thing is sodium borate. Acid, base, or salt? It's a salt. How do I know? It's not an acid. It's not one of the bases I'm familiar with, and it has two names, sodium borate. The two names come from the two ions, the cation and the anion. The cation is the sodium ion, and the anion is the borate ion, and it must be negative. Might be -1, might be -2, might be -3. We'll talk about that in a minute. But it is something I can Google on a practice set. On a quiz, you can also Google. It's just that there's a problem because you may run out of time. If you were Googling, then what is the borate ion? Again, you might run out of time, but you don't have to know the formula because you recognize, tell me you recognize, that the borate ion must be the conjugate of boric acid. So if boric acid is Ha, I can represent the borate ion as A minus, its conjugate, which means I have two things in my beaker. I have a weak acid and a salt. Once I decide I have a salt, I look at the ions and decide if each ion is acidic, basic, or neutral. This guy is neutral, which means I can ignore it. This guy is the conjugate of a weak acid. Which weak acid? Boric acid. So it is basic. Therefore he is basic. He's a weak base. I have two things in my container, boric acid and the borate ion, a weak acid and a weak base. The next question is, are they conjugates or not? Yes, they are conjugates. This is a buffer problem. How do I work a buffer problem? I work a buffer problem with one equilibrium reaction, one ice table, either as the weak acid problem or as the weak base. It doesn't matter which. I'll get the same answer. I want to work it with the easier way to set it up, and the easier way to set it up is to start with that acid because I've got a Ka value. And so I will write the equilibrium reaction for a weak acid. This is the generic reaction for a weak acid. You should know this like the back of your hand. You should be able to spit that up in 5 seconds or less because you see it over and over and over again. And so initially, my weak acid in this problem is 0.55 molarity, and the borate ion's concentration is 0.49 molarity. I have an initial change equilibrium table. I have a Ka value for this weak acid problem. I'm going to put 0 here, minus x plus x plus x. So at equilibrium, it's 0.55 minus x, and 0.49 plus x. So now I have my equation, my Ka, which is 5.4 times 10 to the minus 10, is equal to x times 0.49 plus x divided by 0.55 minus x. I could plug this equation into an algebra solver just straight away and solve for x if I wanted. And if you are comfortable with that and getting familiar with it, go for it. You also can use the approximation method here. That will work with buffer problems 99.9% of the time. Never say always or never, right? But let's plug that into our calculator. I've got my calculator here. Ooh, can I pull it up here? Let's see. Let's see if I can pull it up here. All right. So I've got my calculator. I'm solving for x. All right. So I've got 5.4 times 10. I'm going to use that EE function. It's been a while since I've used this calculator. Where'd it go? Oh, there it is. It's the second function here, EE, negative 10 times 0.55 divided by 0.49 equals, and I get that x is 6.061, do not round, times 10 to the minus 10. If I come back to my problem, let's make this smaller or just get it out of the way. If I come back to my problem, that is the value of x, and x is the H plus concentration. All right. And so what is the pH of? pH is the negative log of that value. And so let me pull my calculator back up, if I can remember how. There we go. And I want to take the negative log. I've got that answer there on my calculator. Let me take the negative log of that answer. How do I bring that answer back? I know there's a way. There it is. Second function answer equals. And there he is. That pH is 9.21743 ... All right. And we're to report our answer to 2 decimal places. So I will report the pH of 9.22.